Thank you very much. Thank you very much, JP. Thank you very much to GMU Center of Excellence for inviting me for this talk. My name is Milos Malic, as my good colleague JP Alfred said. I'm professor of computer science at VCU. I'm director of VCU Cybersecurity Center. I'm also running another center that I'll take a few minutes to reflect on, known as Covell Center for Advanced Computing. And without further ado, let's go with the slides. So when I landed this as a IEEE president, I get to travel quite a bit, and one of the airports I landed at this summer was Athens, and they were advertising Athens or Greece, and I found it very interesting that they reflect on hacking or Trojan horse, essentially saying, at least in my view, that cybersecurity is really goes back to as long as humans have been around. Why am I starting with this? Well, my work with relative to energy and national labs, I've worked with national labs for probably good 20 years, um, mostly with Idaho National Lab. The critical issue is energy and power, because energy, you lose energy, you lose power, everything goes down within seconds, minutes, maybe hours if you have generators, but that's about it. But the critical issue here is how do you secure energy, and many of the labs have that motto, energy security, which may mean different things: securing energy, or making energy secure, or just being able to provide resilient sources of energy. So I'm running a BC Cybersecurity Center. That center has 4 colleges and number of departments underneath. And as part of our activities, we have various events, speaker series. We hosted the largest FBI regional collegiate academy. Actually, it is the first one in Virginia, and as various other events. Our center is actually has two centers underneath. One is for research, one is for cyber defense, and these are certified by DHS and NSA. A little bit about myself. I am running 2 centers. I am IEEE fellow, fellow CCI, and senior National Academy Inventors member. My American life, last 20 years plus, have been tied to national labs and securing the grid. There are many aspects when it comes to securing grid. Talking about energy sources, from hydro, nuclear, coal to others, renewables, of course, then transmission of energy, then usage of energy. And when we say usage, that also means the optimization of usage. And I'll speak a little bit to some of those, for example, buildings, and also fuel efficiency for transportation. It turns out that about 80% of all energy produced in U.S. goes to buildings and transportation. So these are 2 very big ticket items. If we can secure and optimize those, we are probably making the biggest effect on big infrastructures. I want to mention about 14, 15 years ago, I started the colleagues from INL, a Congress that evolved now into Resilience Week. It's, I believe, in 15th year. Resilience Week actually has number of tracks or topical areas, and that's what's really important about resilience. Resilience deals with, of course, computer science, the angle of cyber communication, securing those. Also, human factors, very important, networking, and many others. By the way, um, quite some time ago, probably 10 years ago, we organized the first NSF workshop on resilience. And as one of the big conclusions out of that symposium was that resilience really goes way beyond security, and it typically deals with intelligent reaction to maintain some kind of minimum operational level of critical infrastructures. Intelligent also means that very frequently and in recent years more so, AI is important part of it. And another very important aspect that came out of that workshop was that resilience really needs to be focused on cascading effect. And in many cases, from benign to malicious faults or attacks, we realized that very frequently that cascading effect is what really matters. For example, if we lose power, how will that affect transportation? How will that affect water? How will that affect hospitals? How will that affect manufacturing, et cetera, et cetera? So I will reflect on security, resilience, and similar topics a little bit more as we go. Um, in the world of national labs, I'm probably known best by our R&D 2018 award. This one was commercialized by DHS S&T and put into production. Now it's advertised under the name OT Optics, and it represents the first industry first AI-driven intrusion detection system for serial connected control systems. Really, um, uh, legacy systems which you will most frequently see when it comes to energy systems. So AI, I've been in AI for quite some time. Started back in Europe and continued in US. I will speak to AI as a powerful tool, as is any powerful technique or tool or technology. Unfortunately, can be used in nefarious ways as well. And at one point, I wanted to see what happens in the regular month relative to AI, and I never changed this slide. But at one point, what happened with AI was that AI agent beat actually AI true AI pilot and of course in simulation, and knowing how much it takes to train a pilot that speaks volumes. We when it comes to AI, it's very important to define what AI is. People have different definitions. Um, when I teach AI class, we go into discussion and usually we settle on AI being um, ability to learn. And that's what's critical about AI. If you give the system ability to learn, you're giving one of the s- biggest powers there are. Um, the ability to learn really means to gain new knowledge, to learn as you go. And we see that in autonomous vehicles. We see that in many devices these days. Um, and but why is AI not more ubiquitously uh, involved when it comes to um, workforce development, when it comes to real industry? There's quite a bit of hesitance, and usually that's because of lack of trust in AI. And this was illustrated by McKinsey's consulting results some years ago. They showed that uh, future adopters with highest additions will really be Singapore, India, and China. So it's a big lesson to what the future brings and how can we address this. This one is a short video from humans where the um, anthropomorphical human-like robot makes a decision in case there's a dangerous activity to be executed. For example, here it's taking a hot dish out of the oven and it decides to hurt the mother instead of a child because it's calculated at risk. Of course, mother takes it personally, and this is well known problem in AI, and something that researchers have been wrestling for years now. Many big names raise red flags when it comes to AI. I will mention a little bit about what biological or artificial neuron actually have. They have number of inputs that are weighted, meaning they control how much a signal is coming into a neuron. And as a part of every neuron, we have something called bias input. So when people talk about bias, they typically mean bias is something to be avoided. Technically, in computer science, we always have bias as part of AI. The trick is, can we keep that bias in check? Can we manage it? Can we make sure that that bias does not cross the line and does not make the system unfair or biased, etc. So what we do in research when it comes to bias, how we fight this bias, we typically use some kind of true irrefutable knowledge. For example, physics-based knowledge. For example, we know if we drop a pen that it's not going to go flying, but it's going to, because of the gravity, will go to the ground. So if we know physics well enough, we can keep systems in check. And AI is typically AI driven. So AI may or may not be truly representing systems. So what we typically do is we introduce something called inductive bias to fight bad bias. This is one illustration. I'll talk about papers. These papers are supported by various grants that I can talk to limited extent, but I can speak to our papers completely. And this one illustrates the idea of physics-informed data-driven techniques. Now, I will mention another challenge with AI. AI typically learns from cyber-physical systems or data or learns from humans. And this is the problem, both for cyber-physical systems and humans, because they're all imperfect, especially humans. So if AI learns from humans or imperfect systems, it is not surprising that AI is actually imperfect and it learns to behave in biased, inaccurate, unfair manner. So little illustration of how humans are fallible. There's many in human factors. Human factors are very well represented in national labs because um, national labs deal with real systems that are operated by humans. For example, nuclear control room. And one of the examples how humans are easily fooled is known as perceptual contrast. In other words, if we lift an object, we will be able to somewhat correctly estimate the weight. But if we lift much heavier objects prior, then the next object may seem lighter than it is. And that goes long ways in terms of perception and how humans are tricked to make some decisions that otherwise they wouldn't. And simple example of that is phishing in email. Another big challenge in AI is trust or explainable AI. It started good 10 years ago. One of my students got a doctorate on this topic 7, 8 years ago. And some of the questions that were asked then still stand today. And these questions are really two simple questions. When AI does something correctly, can we explain why it did correctly? Or when AI fails, can we explain why it fails? And you would be surprised when you ask people that have done something well, if you ask them to explain why did they succeed, how little they will be able to speak to it. It seems very simple, but it's not. And finally, another challenge with data is what a couple of years ago was published in Forbes. Forbes published Gartner study that stated that most of the data used in development AI will be synthetic rather than real by 2024. I haven't followed up on what they're publishing now, but here's the problem with AI. we have all those edge devices, all those sensors sitting in cars, in nuclear plants, in hydro plants, in renewable energy sources. We have all that data that's collected by AI, digested and transmitted in some way. So here's the problem. If AI is data driven and AI is very much involved in generation of data, how can we trust that AI because it's at the same time producing data and it's making decision on that data? So these are some of the challenges. I will illustrate briefly some of the work that we have published, and I can easily speak about it. Buildings are, as I said, one of the big ticket items when it comes to energy consumption and stability of grid. Um, at some point, we were talking about smart buildings, but recently, in the last 10 years, we are talking about smart buildings, EVs, and the grid. And the trick here is, can you predict the consumption? Can you predict demand and supply? We all know when demand changes dramatically, that imposes significant challenges for the grid, let alone the pricing that skyrockets. And with this effort, we had several years working on this. We created um, our own sensors that were collecting objective data. We were looking at occupant comfort in buildings, and how can we correlate that with the supply, demand, and the grid. And some of the tricks that you may be aware of are that HVACs can increase humidity and make you feel warmer than it is. So there's many ways that occupant in a building can feel comfortable while actually saving energy at peak times. Um, we use different neural networks at the time. At the time, LSTMs were popular. These days, we have some other uh, more modern algorithms and so on. When it comes to AI, I will also speak a little bit about electric vehicles. Electric vehicles and specifically EV chargers. The trick with EV chargers is that unlike regular gas stations that are co-located with some kind of shops, they're sitting on the street, they're well lit, well, if you will, have some level of security. EV chargers do not. EV chargers are sitting sometimes in the middle of the road. There's no one around, and are in a way open to physical access and bad actors. Similarly, by the way, it goes to renewable energies such as wind turbines and solar panels. These are typically turbines are put on top of some hills. There's so many, they're physically distributed. It's very difficult to physically secure them. Same goes for solar panels, solar farms, and similarly goes for EV chargers. And we've done quite a bit of work on vulnerabilities of renewables such as solar and wind generators. I won't be talking about that, but some of the similar lessons apply here. I will say, for example, EV chargers have frequently are inlet for cool air in order to cool the charger. So what happens if say you have a layer of dry leaves that are blocking that? Very, very similar one, not to go into some more nefarious ones in terms of cyber communication or others. So the trick with EV chargers, as many other technologies, is that we are pushing the physics to a maximum. We are going to regularly, 30, 40, 50, and 70 amperes, but for larger vehicles, heavy duty vehicles, uh, megawatt chargers are being planned. And now we're talking about 250 amperes plus. This is way more than whole streets of houses are using, for example. So what that means is that these cables are liquid cooled, and the margin of error is getting smaller. And this is what we are worried that nefarious actors may capitalize on. So there's quite a bit of research on this. I will mention that we are using physics-based and data-driven AI techniques to fight this, to ensure security and resilience of such systems. Um, Again, physics-based models tell us a lot about what the measurements should be. So if we're able to at least majority of measurements get securely, we'll be able to keep data-driven techniques in order. I will mention a little bit about visualization. Visualization is very important when it comes to power, and it goes back to some events such as TMI accident, 3 Mile Island accident. What happened at that time was that the operator in a nuclear control room, um, at that time, visualization was more of a lights blinking, literally lights blinking. And what happened at that time, I understand, was one of the critical lights was blinking, but it was blinking for quite some time, and some other lights were also confusing the operator. So instead of operator being able to be focused on what was really important at that time, the operator actually missed the important um, flag, and a terrible nuclear accident followed. This is the case still today, and we can see examples of that everywhere where human operators are involved. In a car, for example, if you see a light blinking for quite some time and nothing really terribly happens, you will tend to start ignoring that light, and that's a terrible thing if that light is really indicating mission critical failure. So what I'm trying to say is that when it comes to human operators in mission critical systems such as uh, energy plants, um, the contextual information is very important. The information at this moment, specific information, may be irrelevant, 5 minutes from now. But at this time, you need to always be displaying contextually important information. So we did some review, we did some research on this on cyber and physical metric. And this is from the paper that I can easily display here. And again, visualization is very critical when it comes to AI. I will conclude with a couple of slides here about trust. We have worked on various cybersecurity problems, and we published a paper quite some time ago showing that with deep learning, with most advanced AI techniques today, you can pretty much solve any problem because these algorithms are and advanced computing resources are so powerful. You can solve pretty much any problem. But what we have concluded was that if we are not looking at right features for the algorithm, we will actually get these catastrophic failures when we put such systems in production. So it's really important to look at right features for right reasons and build trust. Um, Finally, I will reflect on the Congress Center for Advanced Computing. I was appointed director of CCAC last year. The CCAC has board members from a number of organizations, academic and industry, and it's as its centerpiece has IBM Z16 supercomputer, and that supercomputer is best known by a chip known as Telum, and Telum actually does real-time AI for fraud detection. And key here is real time. Today, with AI and enough data, enough time, we can model everything. But today, one of the biggest challenges is becoming real time AI. This is from the opening on 27th and few images from Visit to Watson, IBM Watson, and Quantum 1 and Quantum 2. And reflecting on what Shannon was speaking about just a few minutes ago, um, our center is hosted, is sitting at QTS, one of the top U.S. data centers, but Virginia in general is actually sitting on the fastest transatlantic cables coming from South America, coming from Europe, etc. So uh, really, this is why Virginia is becoming dubbed as New Silicon Valley, because there's so many data centers and based on ultra fast connections with the rest of the world. Um, we see Virginia as growing in this direction tremendously in following years. And but these data centers are huge consumers of water energy in order, especially when it comes to AI driven um, platforms. And I will end with the slide that I like to end with. When it comes to AI, there's a lot of things that we tend to trust over time, even though we do not understand. And a reflection on that was when Albert Einstein met Charlie Chaplin, and Einstein told Charlie Chaplin, "What I admire most about your art is universality. You do not say a word, and yet the world understands you." Well, Charlie Chaplin replied, "It's true, but your fame is even greater. The world admires you, and nobody understands you." So, very frequently, especially in recent years, we tend to admire AI, even though we don't understand it, which probably is the way it has to be when with new technologies. But AI is developing much faster than any other technological breakthrough in the past. So this brings me to a final message of responsible AI. We need to use AI responsibly. We need to understand that AI may use information we provide in ways that we may not know. And we also need to recognize that training AI is the responsibility of all of us. AI learns from us. ChatGPT learns from inputs we provide, and we are an interesting part of future of AI, and hence we need to use it responsibly. Thank you very much, JP. Thank you very much to Mason Center of Excellence, Cyber Resilience, and I'll be happy to take questions if any. Thank you very much again.